All right, so we've got a lot of questions over the weekend. So right now what I'm trying to find is the formula sheet that you're going to be given for test one. But the first question comes from optical activity, so give you just a minute to find that formula sheet. This is the formula sheet that you'll be provided with on all organic exams. Just remember where I saved it in the actual course. Come on, where are you? Fine, do this. Anyway, goodness sakes. Come on, formula for optical activity. Almost there, I promise. There we go. So for optical activity, we have an alpha equals some reference times L times C times the percent of antimatter per over 100. This basically, since percentage here is given, for the EE should be a less than one number, but we typically report percentages, so this dividing just gets rid of that percentage. Now, a few notes on this just to make sure I'm telling you correctly. Some formulas differ on this, which is why I need to check it. There was a bug in the notes for a long time about L and C being given different numbers for different units. So L here is the path length in decimeters. And that's just centimeters divided by 10. And our concentration here divided by grams per milliliters. So the number of grams you have divided by the milliliters, and that will get you to this formula. So, question that got asked. Page 14 study guide, there's a chart for optical activity. I have trouble finding the percent EE value missing, and perhaps I may just not know how to do it. So in the packets, come here. Page 14. Basically, if you look at this page, let me swap it out. Let's take a look at it here. It's this formula just with terms missing. So we have the alpha equals the alpha D times mass of the substance divided by the volume. That'll give you the concentration, the path length in centimeters, and the EE. So all you're basically doing here is just rearranging this formula. So for the first one, you're given the alpha D is 112. You're given that, so the problems here are done in columns. You're given that the mass of the substance here, the concentration, is 1 gram per 1 milliliter. Wow, that's really concentrated. So C here is 1. Your path length is 1 centimeter or 0.1 decimeters. And the enantiomeric purity here is 100%. So you get 112 times 0.1 times 1 divided by 1, so you should get an optical rotation here of 11.2 degrees, which makes sense. You're kind of at 1/10 of a normal concentration. How did I get that 0.1? Oh yeah, the length in decimeters. So the confusion here may actually come from the key. The key was originally written for centimeters. Ah, that's what it is. So the key here was originally written in centimeters. That path length there should actually be dms, not cms. So if you're looking at the key and you can't figure out why everything is to be multiplied by 10, that's actually just a typo in it. That length where it says centimeters, it actually means decimeters. So that's probably why you're probably all getting off by a factor of 10. That's just a correction that keeps popping up in this key. Like, it just is a mistake that's been propagating through all these versions. The path length, the key is in those decimal study packets are actually supposed to be decimeters, not centimeters. Originally, when I taught this course, I tried to get away from the decimeter measurement. It is an incredibly obnoxious measurement, but it permeates so much of the books now, because originally it was done with decimeter tubes. Because of that, all the formulas are written in decimeters. The concentration itself is kind of a weird formula in old books. But because all the formulas are in decimeters, there is a conversion factor that goes into play with this formula if you try to get out of decimeters per milliliter. And so because of that, we're just kind of stuck with this decimeter. I haven't found a good way to get it out of the notes because the book works in decimeters and the homework works in decimeters, and so I'm forced to work in decimeters. But again, if you're curious why you seem to be off by a factor of 10 to the solution key, that's because that's just a typo. It says centimeters because when this packet was first made, it was in centimeters. It's actually supposed to be in decimeters. Next question, questions 14 through 15, optical activity. It's kind of the same thing. Again, if you're finding yourself off by a factor of 10, it's because that path length is supposed to be dm, not cm. For question 15, on page 15, a racemic mixture of alpha glucose. This is actually one, if you understand what EE is, you don't even need a calculator to do that problem. So when it says a racemic mixture, what racemic means is that there are equal amounts of the D and the L or the R and the S forms of this given molecule. So if you have a racemic mixture, concentration of R equals the concentration S. So if you're working with sugar, CD equals CL. And so in both cases, EE is 0. And so for question 14, you don't even need to pull out a calculator. If it's a racemic mixture, the optical activity is 0. The second one, you receive a mixture of camphor, claiming to be an antibacterial purity, dissolve 1 gram of camphor in 10 milliliters of water and measures optical rotation of the polarimeter to be with path length of 2 decimeters. From your results, you find the optical activity 7.0 degrees. The substance actually pure? If not, what is the EE? So for that question, we have alpha equals alpha D times L times the concentration times the percent EE over 100. We know in this case alpha is 7.08 degrees. We know that the alpha D from that table, so it gives you on the table on page 14, camphor has an alpha D of 44.26. Path length is 2 decimeters. The concentration given to you in this problem, you have 1 gram in 10 mLs times the EE over 100. So this ends up being 0.1. So we get 8.852 times the EE over 100. So now if I solve for the percent EE, so 7.08 equals 8.852 times EE over 100. Off the bat, you should tell this isn't a pure compound because these two numbers should equal each other for EE be 100. If I have 7.08 divided by 8.852, I get roughly 80% purity. So all this is doing on the page 15 is just getting you to rearrange this formula. And if I look at the key, yeah, 80%. All right, last question. You're charged with determining if an unknown sample is alpha or beta glucose. So you devise an experiment where your sample of glucose is converted purely to the D form. After making the material, you dissolve 1 gram of the synthesized D-glucose in 10 milliliters of water and measure its optical timidity and polarimeter with path length of 1 decimeter. Your reserved optical activity is alpha is 11.2 degrees. Assuming you really did make an anatomically pure compound, you have alpha or beta glucose. So, same formula. And your measured optical activity here is 11.2 degrees. Here we don't know if we have the alpha or beta. So your value for alpha D here is going to be based on whether or not you have an cool. So if you go back up to the top on the previous table, you have alpha and D glucose. Alpha glucose here has an optical activity of 112. Beta D glucose, this is 18.74. But again, we don't know this, so we know that whatever our sample is, it's pure. So it's 100% divided by 100. We know the path length here is 1 decimeter. And we know the concentration is 1 gram per 10 ml. So we have 11.2 equals the alpha D times 1 times 0.1 times 1. Because again, we're going to assume here, it tells you in the problem, assume that you have a pure compound. So you either made alpha or beta. It's 100% pure, but you don't know which one. We measure the optical activity, we know the path length, we know the concentration. So this tells us here that the alpha D here is 112. Well, that only corresponds to the alpha form. So by doing this polarimetry measurement and making the assumptions we're told to make in the problem, we're pretty sure we have the alpha form because it's the only one that would be consistent. If we ended up with 1.874 degrees, we would say that we probably made this form because when we worked it out, we get 18.74 as the reference. So the last problem is basically getting you to solve for the alpha D and comparing it to the alpha and the beta tables that are found, the alpha and beta glucose forms that are found in the table on the page before it. So that's all these problems are doing, are basically getting you to rearrange to solve for an unknown variable. All right, that question's done. Questions 43, 44, and 45 on the homework. All right, this is also organic chemistry. What is the absolute configuration of minus bromochlorofluoromethane? Oh, the absolute configuration of minus R bromochlorofluoromethane is R. Which one is R? Br. So basically it is, okay. So in this question, you're given bromochlorofluoromethane. So this has formula of CClBrFH. And we're looking for the R form here. And it's asking you which of these meet the criteria for the R form. So we have F, Cl, H, that's Br. All right, so the reason this question exists is actually testing a whole bunch of information at the same time. One is your ability to do RS configurations. The other is to be able to take these types of drawings and manipulate them in order to do either a Fisher projection or to do the RS. So we'll start with this one. This is the easiest. So we rank them in terms of atomic weight. So bromine's the heaviest, chlorine, fluorine, and hydrogen's always last. Now with the Fisher projection, the rapid way we can figure out if it's RS, we swap the highest and we swap whatever's opposite the lowest priority. So since chlorine's the lowest, we're going to swap with chlorine, and we're going to erase the lowest priority group when it flips over. So this 1, 2, 3, this is counterclockwise. So as drawn, this is the S conformation. So we're looking for the R here. So this is not an option. For this one, hydrogen, 4, 3, 2, 1. Few ways you can do this one. Honestly, the easiest way for me to visualize is I rotate it so the hydrogen goes back. This would give us a fluorine, chlorine, and a bromine. So 1, 2, 3. If I rotate this, this is clockwise, so this is R, so this one works out. The other way you can do this, and I would highly recommend it to you if you're kind of struggling seeing this. Just a minute. Is just to build the model. So let's do fluorine is red, chlorine is blue, bromine here is going to be this pink color, hydrogen is going to be white. So if I build this model, I've got bromine down, fluorine up, chlorine up, hydrogen to the right, bromine down. So this is my structure. So to find the list of the functional groups you need to know, if you go to the Test 1 study packets, specifically go to the link, don't go to the one that's listed in the big paragraph in the comments. If you look at that one, it actually has a list of functional groups. Those would be the functional groups I would memorize. They're going to come up pretty much the rest of the semester, so particularly when we start talking about reactions, when I say it forms a ketone or aldehyde, you do need to know what a ketone or an aldehyde is. All right. So now that I got my model built, I'm going to take it and rotate it so the lowest group is behind. So I've got fluorine, chlorine, bromine. When I look at the rotation, I get an R conformation. This down here, this model down here, I'd recommend the same thing. So we've got fluorine coming up, hydrogen going down, chlorine going to the right, bromine going up. So this is your structure. Again, turn it so this way that you've got the lowest priority group going down. So I've got fluorine, chlorine, bromine. Bromine is 1, fluorine is 3, chlorine is 2. That's a clockwise rotation, so that's also R. This one is actually kind of a Fisher projection turned around. So if you rotate it, you'll end up getting the Fisher projection. But if you can't see that, again, build the model. So you've got bromine and hydrogen, fluorine and chlorine. It really is just this model. So if I take it and rotate it, I get fluorine, bromine, and chlorine. This is also R, which is what it's looking for. So again, all 4 of these are just, yeah, you're welcome. All 4 of these are just simply meant to see, one, if you can convert these to something like a Fisher projection. Honestly, for these 3, the easiest thing to do is build the model and just work with the model. If you're comfortable with the Fisher projection, work with the Fisher projection. Otherwise, you can build this molecule as well and use that to find the RS. But here, I'm getting that the first, second, third, and fourth are all R conformations. Let's see if I'm right. What? Which one did I get wrong? So I've got bromine and hydrogen. Oh, when I built this one, I flipped them by accident. So for this one, I accidentally had the chlorine and fluorine flip. That's why it's actually S. So no, it's only these two that end up giving the R conformation. That was a mistake on my end. All right, next one, 44. Draw the three-dimensional representation of the S enantiomer shown below. Okay, so this program is really picky, and you can probably still be getting it right, and it's just going to nitpick you in terms of the final solution. So here you're asked to give the three-dimensional representation of the S enantiomer of this compound. So off the bat, we need to figure out, like, if as kind of drawn, if this is correct. So hydrogen here is going to be the lowest priority. We've got a carbon, a carbon, carbon. This carbon is bound to 3 hydrogens. It'll put it as group 3. This carbon is bound to another carbon, whereas these two are bound to fluorine. So this would be the number 1, and this will be the number 2. So assuming that these go in opposite directions, if I tilt it up with the hydrogen in the back, it'll look sort of like this. So I've got my third. So basically if I rotate it so that corner's up, I've got my hydrogen in the back. So 1, 2, 3 is definitely the S. So as drawn, this is correct. We just need to put the wedges and dashes. This is where it gets kind of weird with this software. There's actually an interesting history behind all the software for drawing organic chemistry. If you ever look up, there's a code called SMILES. That was like the golden standard for writing organic molecules. SMILES program got gobbled up. It's behind a paywall now, and so we're kind of left with all these knockoff versions of SMILES. So personally, if I were to draw it, I would draw the ring flat, and I would take that three-dimensional ring and I would turn it down so I can build it for you here. So this is the molecule as it is in the program. Personally, the way I would draw it is I would turn it flat, so the triangle's in plane, and then I'd have the hydrogen coming out and the CH3 group going back. So if I try to draw this structure, and I'll switch to the desktop for you, I think odds are it's going to mark this wrong. And honestly, I think it's going to be particular if you don't draw the wedge bond kind of going back. We've got hydrogen, fluorine, fluorine. So if I put that in, that is drawn correctly. Okay, odds are weird, it's kind of marking it correct. So I will tell you, it is a very picky program. And I don't know if the reason I got it right was because I just have gotten so used to the program. That's just the way I think about it now. But for me, that's the easiest way to draw it, is put the triangle in plane. I know that if you try to draw it with like the 2 wedges out and a whole bunch of dashes back, sometimes it likes to ding you for that. But if you've gotten this structure, it's just kind of like dinging you for like no reason. Let me know what your answer is. But that's what I would put down is I would put the cyclopentane ring in plane and then have the wedges and dashes out. But again, you could also draw it like that. And the only thing you'd have to be careful here is make sure that you've actually dragged the bond, so this way you have the hydrogen fluorine up and the methyl and the fluorine down. So it doesn't try to think that you're trying to like put atoms between other atoms. For 45. Draw the three-dimensional representation of the R enantiomer for the molecule below. Well, I guess that means we need to figure out which one's the R enantiomer. So we're given this ketone. And the first thing we need to do is figure out which is, first of all, we need to find the chiral center. So that's not it, not it, not it, not it, not it. Definitely going to be that one. And the next we need to figure out the R. So the thing is, if we pick wrong, we know the S enantiomer is just flipping the wedges and the dashes. So arbitrarily, I'm just going to put the bromine forward and the methyl group back. And we'll see what this looks like. So bromine here weighs the most, is the highest priority. I have a carbon, and a carbon. This carbon has 3 hydrogens. This carbon is bound to another carbon and 2 hydrogens. This carbon is bound to the oxygen twice and bound to another carbon. So now I compare the first point of difference. This weighs less than the 2 oxygens, so this ends up being the lowest priority. The oxygen here is higher than the carbon, so it's the second highest and the third highest. So this is my order. I have my bromine followed by my ketone, followed by my CH2, followed by my CH3. Now, because this CH3 group is pointing back, I can just look at it as is. So if I do this, 1, 2, 3, as drawn, this is the R enantiomer, and that's what it's looking for. So when I draw this in the molecule drawer, that's what I need to draw. So I've got my cyclohexane. I'm going to have a wedge. Again, make sure your dash goes off to the right. Oops. And then I got a double bound oxygen. There you go. And again, I think it does nitpick you. If you try to put the methyl group on the left, it will probably ding you and say that you've got it in the wrong place. Again, if you're getting to this answer, you clearly understand it. It's just issues of formatting. And that is it for questions. So I've got the chat open. If you've got more questions, please feel free to ask them in the chat. Otherwise, I need to take care of a few things. But again, please feel free to ask questions. These are office hours. These are not lessons or lectures, so I don't have anything prepared. So yes, I am a chemistry teacher. So I do Chem 1, Chem 2, Organic 1, Organic 2. So you got any questions for me regarding chemistry or science in general? About enthalpy. I think I actually do have videos about enthalpy. Hold on, let me check. Um, So I've got this video on Hess's law, so all the laws associated with working with enthalpy. And then this is just a video qualitatively describing what enthalpy is and the different types of enthalpy. I don't teach physics, but I do understand physics 1 and physics 2. So if you got questions about physics, I don't have any videos in that, but I can definitely see what questions of yours I can answer. Electromagnetism, that I might be able to answer a few questions about. Yeah, feel free. I'll see what, I don't know how many I can answer off the top of my head, but we can see. Editing files really quick. So technically, yes. So this goes to Einstein's idea of relativity, that it's more of a reference frame. So let's say we have some charged particle, we'll just call it an electron, and we have ourselves as observers. And if we impart a velocity, we have two scenarios where we impart a velocity to the electron, or we have a situation where the observer is moving. And the question is, if we know in this scenario that the electron is creating a electric field due to its movement, do we see an electric field here? And the answer is yes, because if we look at this electromagnetic field that we're producing is a result of gradients of the strength of that electric field. So the charge here, or the force felt by the charge, Q1, Q2 over 4 pi epsilon naught r squared, our distance to this is going to change if it's moving or if we're moving. So the reason we're getting this electromagnetic force is that we're changing the strength of the magnetic field that's observed. So this is what's considered a relativistic thing. It's because objectively these two scenarios look the same. And to kind of illustrate this point, let's say we had the person and the electron sitting on a block, and we have a second observer here who's stationary. As the block moves, these two don't change their distances to each other. So from their point of view, this does not see a magnetic field change because their distance to each other hasn't been affected. But as this block moves, this observer sees a magnetic field because the electron itself is moving with regard to its stationary standpoint. So these two don't observe a magnetic field relative to each other because they're both moving at the same speed in the same direction. So the electron seems stationary. But this observer definitely sees a magnetic field because the electron is moving. So the movement here just has to be relative, and it doesn't matter who's moving. The only point is that they have relatively different velocities. In the case for the electrons moving, from the observer thinks they're standing still, whereas the electron looks like it's moving. From the electron's point of view, it's standing still and the observer is moving. I'm sorry, it's not relativism, it's reference frame. So who moves doesn't matter. That's an issue of the reference frame. But as far as it depends. So let's have our electron sitting on the block, and let's have our device. So we've got some electromagnetic field measuring device, and we've got two of them. And let's actually have three of them. So the block itself is moving, and we'll say that this detector is moving. And because this block is moving, this detector doesn't see these two other detectors. It sees the electrons moving, and so it thinks it detects a magnetic field because the electron's moving. These two are stationary to each other, so this one will detect a magnetic field. This one won't, because it and the electron are moving at the same speed. So the magnetic field, the charge felt by that electron doesn't change as this block moves. This block, however, is moving away from the electron. So this one also detects a magnetic field, and it detects a magnetic field in the opposite direction of this one because this one's point of view says that the electron is actually moving to the right, or moving, sorry, got it backwards. Now I got it correct. So this one actually detects a magnetic field in the opposite direction because the electron's moving away from it, whereas this sees the electron moving towards it. So it all depends on the reference frame of the detector. If the detector and the electron have the same, basically from their points of view, are moving at the same speed at the same direction, this detector will not detect a magnetic field due to this electron. But these two detectors are moving relative to the reference frame of the electron. And so they both detect a magnetic field. Because the electron is coming towards this one, it detects a magnetic field of one direction. Because this one is moving away from the electron, it detects a magnetic field of the opposite direction. Yeah, you're welcome. I'm in the United States. It's not just hypothetical, it's actually fairly disproven. So hybridization is not the same thing. So there are two theories here. There's Lewis theory, and then there's molecular orbital theory. Or MOT. So Lewis theory predates SPDF orbitals, and this hybridization was kind of a back way. Hybridization was kind of a way to try to backtrack what was predicted by molecular orbital theory. So hybridization here is going to say molecular orbitals are a linear average of atomic orbitals. So if we have an s and a p orbital coming together to make a bond, the bond that gets formed is an average of s and p for both atoms. In this case, let's say we have a carbon and a hydrogen. So first of all, that's not right. That doesn't make any sense to say that these two would share electrons equally. Molecular orbital theory says that molecular orbitals are formed by a linear combination. So we've got some coefficient on the S and some coefficient on the P for the carbon and the hydrogen. The trouble with this is that in order to figure out what those coefficients are, we'd actually have to solve Schrodinger's wave equation. So you'd have to solve this equation, minimizing this E term, in order to find out what the wave function was of all the individual atomic orbitals. So our wave function here is the sum of the coefficient on each atomic orbital. So this is the correct form, and the way we know this, one, we have the theoretical side, and so yeah, this has kind of been done at length with computers. We can minimize these functionals and we can get a really good idea as to what the wave function looks like. And the second is that we verify this experimentally. So we can actually predict what the energy here based on these atomic orbitals, measure what we'd expect for the energy of those orbitals, and actually get pretty close to what the right answer is, what the measured energy is. So that's how we know that this is true, is that we have a theory to justify it, and we have experiments that agree with what the theory predicts. But hybridization here is kind of a myth. There's two things that don't happen here with hybridization. First, we get an average, which we know doesn't happen. The second is that we don't get antibonding. So with hybridization, we don't predict that there are orbitals that if you add electrons actually destabilize the molecule. We know this happens because this is how oxygen and hydrogen dissociate on the surface of metals. So this theory provides no framework for explaining why metals can dissociate covalent bonds. This does because it says not only is there a linear combination, so you'll have the alpha plus the beta on the p, we'll also have the other combination where they're subtracted. So this is where your bonding comes from, and this is where your antibonding comes from. So not only do we get bonding orbitals with molecular theory, we get antibonding orbitals as well. And because we get those antibonding orbitals, we can suddenly explain band gap theory, we can explain how gases dissociate on metals. We get a lot of things that do not come from hybridization. So that's why we know the theory is correct. This is very easy to do. It makes bad predictions. This is super hard to do. All right, so that's the end of the live streams. Again, always free to come ask questions, even if they're not related to the course. I need to head out and get some work done. So again, next live stream, Thursday at 9 a.m., and I will see y'all then.